Hello, and welcome back to Paleozoic PCs, where prehistoric computers walk the earth. I was also going to wish you a happy Septandy, but one look at the timestamp on this video will reveal that I missed the month of September by a mile. Oh well. Today, we're going to be playing with a TRS-80, specifically the 1978 vintage Model I we repaired last year. So, happy Octandy! It's been a while since I've had time for some good old-fashioned hardware hacking, so let's get back to basics and see if we can build something useful for this old computer on our breadboard. Step 1 of building any expansion is getting access to the bus. If you're familiar with the TRS-80 Model I, you know it doesn't have a row of expansion slots, only a single 40-pin bus connector on the back. To break this out for our breadboard expansion, we're going to start with an old 40-pin IDE cable. For this, you want an old 40-pin cable, not the enhanced 80-pin cables with the finer wires. And you'll also want to make sure your cable has all 40-pin presents. Some IDE cables leave out pin 20 as a key pin, which will cause some serious grief. In addition to your IDE cable, we're also going to need a standard 0.1-inch pitch press-fit IDC card edge connector. These are getting a little tricky to find, but they're still out there if you look. In order to keep the wiring run reasonably short, we're going to cut off a stub after the first drive connector and crimp the edge connector onto the short piece we take off. After crimping the card edge connector onto the stump of the IDE cable, which is easier said than done, you'll probably be left wondering how this helps us get from the TRS-80 to the breadboard. Easy peasy. If you order a set of these cheap breadboards off of Amazon or whatever, you'll find they usually come with a set of these colorful jumper wires. Conveniently enough, the pin ends of these wires are the perfect size to plug into a female 40-pin IDC connector. This lets us use the cable we've assembled as a breakout box to go from the TRS-80 to a breadboard using these male-to-male jumper wires. To make life actually running these jumper wires a little easier, I decided to make labels to stick on the cable to help locate the various signals. The colors chosen are fairly arbitrary. Green is for data lines, yellow is the address bus, light blue and orange are the memory and I/O read-write signals, blue and purple are signals that are less likely to be useful, red is signals I almost definitely do not want to touch, and white is grounds. Tandy used a non-standard pin numbering on their edge connector, which is why there are two columns on my labels. The colored column is the pin number that matches the IDC standard, while the white column is Tandy's numbering. The reverse label is the one we're going to tape on next to the pin connector because these pin numbers refer to looking at the back of the cable. For our jumpering, we're going to be wanting to look in toward the holes, so the rows are going to be flipped. After printing the labels, so the tabular data is scaled to exactly 2 inches high, we cut them out and use pieces of clear packing tape to laminate and attach them. I'll go ahead and attach the non-flip version to the computer end of the plug just for reference. Now that we have our bus connection problem solved, let's actually build a thing. For our first project, we're going to make something that's both incredibly simple, but very useful. A 32K memory upgrade that'll take our 16K TRS-80 keyboard up to the full 48K. For this build, you only need 2 chips. I'm using a Cypress CY7C199 32K static RAM chip. These only cost $2 or $3, and functionally identical parts are available from multiple companies. The other chip is a 74HCT04 inverter, which will act as the address decoder. First thing we do is plant both chips onto our breadboard and wire the VCC 5-volt lines and grounds to the red and blue labeled bus bars. I'm also adding a 10 picofarad, pico, not pico, yes, I heard you there in the back, between the VCC pin and the ground on both chips to act as a bypass cap. The first group of signals we're going to wire to the TRS-80 is the data lines. These connect to pins 11 through 13 and 15 through 19 on the memory chip. Technically, since this is a RAM that's only going to be read and written by the CPU, it wouldn't matter if we just randomly connected those pins to the 8 data lines broken under our bus cable. But since I have bigger plans in mind for this setup, I'm going to take the time to reshuffle the pins at the breakout so the lines are all connected to the matching designation. Next group of signals is the address lines. But before I do them, I'm going to stick some individual jumpers in as placeholders for chip enable, output enable, and write enable signals. These are interleaved with the address lines on the right side of the chip package, and filling them will help make sure that no pins end up on the wrong holes. This is a 32K RAM chip, so there are 15 address lines in total, numbered A0 through A14, and they're arranged in a counterclockwise half ring around the chip, starting from pin 21, which is on the right side there. Using jumper wires torn off in groups of 4, we'll simply match the signals from the chip to the TRS-80 breakout. The address lines are scattered all over on the TRS-80 end, so it's somewhat picky work, but it goes pretty easily. The last few pins will start getting a little hard to insert as the connector fills up, but there is room for them. The jumper wires ends are built for the same 0.1 inch pitch as the IDC connector in the breadboard. After all the address lines up to A14 are in place, you can then connect the write enable and output enable signals on the chip to memory write and memory read on the TRS-80 bus. The signaling the TRS-80 provides are directly compatible with this chip. All that remains is the chip enable signal, which is used to tell the memory chip that the computer would specifically like to read or write to it in particular. To supply that signal, we're going to connect CE on the RAM chip to the first output of our 74 HCT04 inverter and A15 from the TRS-80 to the input. So how does this work? Well, in a TRS-80 with 16K of RAM, all the memory installed in the keyboard is in the bottom half of the total 64K of address space available to the CPU. The first 16K is taken up by the 12K of basic ROMs, the memory map keyboard and screen memory, and some reserved I/O space. And the second 16K is the dynamic RAM installed inside the keyboard. This leaves the top 32K empty. If you're familiar with binary, you know that when the CPU is in the lower 32K of memory space, the A15 line will be a logical 0 or low, and when it is in the top 32K, it's going to be a 1 or logic high. Since this chip has enough memory to fill the entire unused 32K, then it follows that all we need to do is enable the chip whenever A15 is a 1. If the chip select line would activate the chip when it sees a logic high, then we'd be done. We'd just connect A15 directly to it. But since most logic chip selects are active low, we need to invert the state of A15. So when CE goes low, when A15 is high. And that's all we need. If the computer's address bus indicates an address with A15 set high, then the memory chip will enable itself to drive the bus or answer a write request when the TRS-80's memory read or write signals also go active low. When these conditions are not met, the memory chip will simply stay asleep. The last thing I'm doing here is wiring the 5 unused inputs of the hex inverter to a 5-volt pull-up resistor. Strictly speaking, that probably will not matter, but it's generally considered good practice not to leave inputs on TTL chips floating. The other thing I'm doing here is connecting the power supply and applying power to honestly make sure smoke doesn't come out of it. Since the chips are cool and everything looks all right, let's try it on the computer. Plugging into the computer might have been a little easier said than done. A brand new edge connector like this can be really hard to plug in the first time. But anyway, now that we've got that in there, let's go ahead and try it out. So for the first power up, I'm going to just turn on the computer with the power supply supplying the breadboard turned off. So we go ahead and turn it on, and our HDMI adapter there wakes up slowly. So we're going to print mem, and we get 15572, which is the correct answer for a 16K TRS-80. So fingers crossed, we turn on my crazy bench power supply, power it up. We get memory size. So after hitting enter, it takes a little bit longer to get the prompt, which is a good sign. And everything's great. We have the correct answer for a 48K level 2 TRS-80. So now we're just loading a couple things to make sure the new memory works. So the first thing I'm going to try is the little basic intro graphics thing that you saw at the beginning, where I have my Paleozoic PCs bouncing back and forth. This is a pretty short basic program, so it doesn't prove a lot, but it does use a string packing technique to do the bouncing, which means that it does exercise the top of memory a little bit, because that's where BASIC stores strings. So this next thing I'm doing is I'm loading a machine language game. I found it on a TRS-80 download site that had cassette images. The game is called Penetrator, and it requires at least 32K. So if this RAM wasn't working, this game wouldn't work. So I sped up this footage a lot, because a 32K game like this takes the better part of 5 minutes to load over the TRS-80's cassette system. So yeah, tried to save you a little pain there. But finally, it's loaded. So then you just hit the slash to execute from the built-in jump location in the file, and voila, Penetrator. So I'll go ahead and end the video here because, I mean, I have some footage of myself playing the game, but I seriously suck at this game. But I have played with this expansion for a few hours, and it works perfectly. I mean, obviously, it's not particularly practical to just leave a breadboard hanging off the back of your computer like this, but it does work. And this same circuit could be easily translated into a small circuit board that could be built for just a few dollars. But anyway, like I said earlier in the video, I have bigger plans for connecting things to this TRS-80. So hopefully, life allowing, we'll be able to play with that some more soon. So thank you for watching. Have a good day.